So the discrete versus continuous formulas, you could see them here previously. For discrete, we used a sum notation. For continuous distributions, we're going to use an integral. Something I want you to watch out for, this xi means the leftmost value of x in a picture will show. So it's the integral limit. It's the limit of integration, whereas this xi is the position of the ith mass. So this is an integration limit, x initial, etc. Another way to write that, you could use total mass instead. If we want to work with this, let's see our formula again. Oftentimes, people just pop out that 1 over total mass in this way. So capital M represents total mass. To work with it, what you need to do is we've got to get this dm into a dx somehow so you can do an integral. So first thing you usually do is relate dm to volume. So a dm is called the mass of a slice. So we got to get that involved, and we can use a density equation. That looks like this. More on that later. And generally, we then use the geometry of the object to relate the slice volume. So this is the slice volume dv. We relate that to dx so we can do an x integral. Excuse me. Usually you do that with a picture, and you have to figure that out using some math. More on that later. Don't forget to determine the limits of integration, x final and x initial. Moving on. Here's a problem, example 9.29 from Physics Workbook Volume 2. We're going to do all these parts in a separate slide, so let's start with part A. So in this case, we've got, you can hit pause at any time to try and guess what I'm going to do before I do it. I don't want to say that all the time. So anytime you want, just hit pause and see if you can beat me to the punch. So check out some interesting things here in our figure. We've got some height, length, form, and it's got its mass. Notice that X points out of the page, J hat is to the right. This is a little bit different, but it is sometimes used. If you could see my hand in the video, I hat's coming out of the page, and then when my fingers curl, I don't know if you could see that at all. When my fingers curl this way, notice my thumb points up. So I goes to J, goes to K. Sorry if you can't see that. In this case, what are we doing? We're going to add up the mass of this slice, the mass of this slice, the mass of this slice, and we're taking a weighted average. That's what center of mass is, just like weighted grades, weighted average. When we add all those up, we should get the average going left-right. In this case, that's J hat. There's an easier way to see this. We see that the slice has some thickness dy over here. Well, if you have a dy, you're going to have a y integral. You're going to get y center mass. Moving on. We oftentimes are told the mass, and given a picture of the object, we know its shape, and we need to get the density. Well, density is mass over volume. So if we know that, take a guess what it should be. Here we go. The total volume of this is, there's the area of the front face, there's the width going into the page. So one thing you could do, 2 over 2, that's just multiplying by 1, that cancels out the half, so we get that result. Now if I want to get the height of the slice, by height of the slice I mean this thing right here that's blinking. So I want you to figure out that height. I notice that this seems to be varying linearly. This is a line, right? So if that's varying linearly, I'm going to write down the equation of a line. Slice height is slope y plus intercept. So again, that's saying that the slice height is varying as y varies. You can take your guess. Rise over run, there we go. And it turns out you could factor out that h and make it look a little bit cleaner. This will be a nice thing later. We'd have to factor it out eventually no matter what. Now if I need to get the mass of the slice, again, I see this slice right here. I want to get the mass of that rectangular chunk. Okay, so if I want to do that, how am I going to do that? I know the density equation will relate mass and volume. It's pretty easy to get the volume of a rectangle, so I could do that with the slice mass is density times slice volume. So notice the density equation works for the whole triangular solid or just the slice that we're looking at. So if dm equals rho dv, I just need to compute the slice volume using these dimensions over here. Now, one thing that's one common mistake is notice that the slice height is z, not h. So we need the slice area, that dark blue. The area is going to be, let's see, that's z times w, and then the thickness is dy. We had an equation for z from the previous page, so this came from the previous page, and notice factoring that h out is kind of convenient. If I plug this in right here, what do we get? Well, when I plug that in, this is the density, this is this, and notice HW cancels out, so that's why I factored out that H, it cancels out. Moving on. We wanted to find the horizontal location of the center of mass. Well, let's get to it. We've got an integral. In this case, horizontal means y. Again, in this case, it's a little bit different. We decided to call j hat to the right. It's not, whatever it is. So take a second. What do you think the limits of integration are? That's what I found. Again, this dm, this is all dm from the previous slide. That's dm. Over here, this y right here came from the equation definition. In the center of mass, there's a y in the numerator. The limits, the smallest possible value of y is actually right here. Whoops, sorry. Smallest possible value of y is right here at the center, which is y equals 0, and the largest is out here at y equals L. If you keep going, you can go on and on. You should do the integral. I'm going to race through it here to get through the video, so you could do it on your own. One thing you should always do is check the units. And in this case, L over 3, that has units of meters. L has a unit of length. Well, a center of mass position should also have units of length. And at any step in here, it could be good practice just to check the units at any one step. For example, right here, notice this thing right here has no units, meters over meters, and this has units of meters. This has units of meters, and this also has units of meters, and so does this. So notice these two combine to make meters times meters divided by meters. I get meters. It still works. A fun little puzzle. Basically, do I have the same amount of mass over here as I do all the way over here? Remember, the center mass is actually right here at about L over 3. That's my attempt to eyeball it. So we know the center mass position is right there. So if I just made a cut right there on this thing and sliced it up like that, which side would have more mass, the left or the right? Take your guess. Let's hit it. Your gut instinct is probably to think they're the same, just not true. It's not true in general either. So if you check the volumes, you could do this math yourself. You could easily verify these add up and find out, oh my gosh, there's more mass on the left side than the right. You could work that out on your own if you want. There's reasons why. I need to move on to keep this video short. We want to get the x, y, z coordinates of the center of mass. So we've already figured out the y coordinate is somewhere right around in here, right? 1/3 of the way. So again, this is L over 3. So now, how do I get the other ones? Well, if you want, you could actually say, well, wait a minute, a right triangle, we know it's 1/3 of the way from the fat end. If I had integrated, I could just literally rotate that triangle or rotate my axis of integration. I could have integrated this way. It's the same problem. And so you should find eventually that the vertical coordinate, which I believe is on the k hat, should be h over 3. Furthermore, I think it's probably pretty easy for you to see by symmetry that the center mass should lie somewhere on this line going into the page, because there's just as much mass, because of the symmetry of the situation. We expect that to lie there. So if you want to see the math for this, instead of redoing all the math, we'll just know that anytime you have a triangle that's a right triangle, we know the center of mass is 1/3 from the fat end. That's how I know z center mass. And just by symmetry, we can go into the page. We expect it's w over 2. Remember, sometimes you get negatives. So that just implies that it's into the page in this case, because we said out of the page was positive I hat. All right. So there's the center of mass position. What if? What if you had a 1D object instead of a 3D? How would this be different? Okay, we kind of did the most complicated way. Let's see what happens if we have a simpler problem, a 1D. Well, what we usually do is we use this term lambda right here. So that's a linear mass density with units of kilograms per meter. You could check the units. ds is some infinitesimal length. I'll show you some pictures in a second. But to be clear, if you have uniform, again, if it's uniform, more on non-uniform after this problem, we have total mass per total length. Okay, here's a picture of a rod extending to the right. ds is a small unit of length to the right. That's why it becomes dx. If we were going up, it would be dy. And then if we had an arc or a ring, you could see it would look like this. I actually have a little blow up here to make that better. And so notice down here, here's the radius that goes from the origin out to the arc. ds is the infinitesimal arc length. d theta is the angle right here. So this d theta is different than this angle theta. Theta is to the start of the arc, and d theta is the angle between the ends of the arc. So notice there's a big difference between theta and d theta. If you had a 2D problem, it's pretty similar. There's a few subtle differences. One, we use a different symbol here. We're going to use sigma, and we use dA instead of ds. We need mass relates to a mass area density with kilograms per meter squared times an area. Notice the units check out. If you have uniform, again, if it's uniform, then we can use total mass and total area. So if you had a plate, oh, I lost my pictures there. Let's just put it all up. Sorry about that. So if we look at this, you could see right here, here's an example. Here's a function. Let's say y is some function of x. What you need to do to get the x center of mass is we're going to slice it vertically so that you get a dx involved. If you get a dx involved in your integral, you'll get an x center of mass. So before you can plug this in and integrate, so I want to use this up here in this formula. But if I'm going to plug it in, first I need to figure out y of x and shove that in right there so that I have something to do an integral with. Okay. And similarly, you could do this the other way. There is one extra step. You need to get y of x again, but then you rearrange it and solve it for x before you plug in, because again, we need x in this case. So you would figure out y as a function of x, you would rearrange it and solve it for x, and then figure that out and shove that in and do the integral. What if it has non-uniform density? This is kind of the last trick. So let's restrict ourselves to a 1D problem just for now, just to keep it simple. You could do a 2D or a 3D with non-uniform as well. So in this case, lambda is still linear mass density. It's just not constant anymore. We still have kilograms per meter. Usually that would be some function given in the problem. And you might have some constants now. So for example, let me see if I have a picture here. There we do. So look at this. In this case, lambda naught represents the value of density when x equals 0. If x is equal to 0, all we get is lambda naught. So lambda naught must be the density at this point. That's lambda naught right there. And then as x gets larger, whether it's larger positive number or a larger negative number, we see it should get more dense. So as I get to a larger negative number, it gets a little bit more dense. There's a little bit more green. As I go to a larger positive number, we go out much farther and see it gets much darker, much more dense. So notice you don't have to have symmetric limits. All this math still works. First thing you want to do is get the units for these things. If you want to figure out the units for alpha, I'll write it out really quick, see if you can beat me to it. So the units of alpha basically, is it kilograms, is it meters? All right, I'm having trouble writing 3. There we go. So that's the units. If you found that, great. You could do the math. If you have trouble, let me know. One thing you got to watch out for in these problems, you need to use this equation to get the total mass. You may have noticed earlier in my triangle problem, I was doing all this extra math in the denominator, and you might have been saying, he gave me mass in the problem. Why didn't he just write m? You're right, I could have done that. but I was hoping to set you up for this. So now you know how to handle a non-uniform case. It's exactly the same as that cumbersome derivation I did. And all you do is you plug in your formula for lambda, and you can do that in the top and the bottom of that crazy integral. It works out. One thing you really got to watch out for, we cannot use this. Can't. It's not equal. So the one common mistake is students often write lambda is m over L. Well, that's not valid anymore. Lambda is this screwball equation. You can't just use this thing down here anymore. And I think that's all we got. So, all right.